Volumes follows on very logically from integration, of course, because volume involves integration. The 2-unit of idea of integration, where we just use the formula, and for that matter, I suppose 3-unit as well, pi times integral of y squared dx or x squared dy, and we could just bang use that formula. That's fine for 2-unit and 3-unit. 4-unit, we're probably more interested in how you build the shape rather than just go and bang straight to the formula. So you don't just quote the formula. And I've got some bad news for you. There's going to be some drawing of pictures, okay? I know you love it. But here's our first one. Volumes by discs and washers. So this is where we're going to slice perpendicular to the rotation, and is pretty much the 2-unit idea, but this is where it comes from. So if we want to go around the x-axis, and so I've got some random function y equals function x, and we're going to integrate, or find the volume, between a and b, I should say. I'm just going to look at one slice. So just like we did when we were looking at area, and we were talking about the sum of all the rectangles, same sort of idea. Each one of those rectangles I'm going to rotate around, and we're going to sum up the volume of all those shapes. So the thickness of my slice here is a change in the x value, so delta x. So if I was to rotate that around, I would get a cylinder. And the thickness of my cylinder is that delta x. The radius of the cylinder would be the y value, which of course is equal to function x. And we get our formula that we're used to seeing, pi times function x squared. But again, we don't just jump to the formula. That's just the area. So the volume, or the change in the volume, would be that area times the change in the x value, or the height of the cylinder. And that's for each individual slice. So to get the overall slice, we're going to sum all the slices. And so here, I guess, is the huge difference, is this line here, where we're saying that, okay, we know that the change in volume will be the area times the change in the x values. And then we're saying, well, okay, if we add all of these slices together. So we want the limit as that thickness of the slice approaches 0. And we're summing up all the slices from A to B of our change in volume formula that we just worked out. And that is what turns out to be our pi times the integral of function x squared dx that we used to see. And I guess from that point on, it becomes like our standard 2-unit, 3-unit volume question. So if it was about the y-axis, we'd see a very similar thing. Random function, so y is function x, but my slice now, because it's going to be perpendicular, I said, to the axis of rotation. The axis of rotation in this case is the y-axis, and so the slice is perpendicular. The slice is going horizontal. So let's put that slice in. There it is. And we're going from C to D, but now the thickness would be the change in the y value. So there's my cylinder. The radius, though, is x, so I need to rearrange my function. At the moment, it's in terms of, as with y being the subject. I need to make x the subject. So I'd rearrange it, and x would be some other function of y. And so the area of that face, the cross-sectional face of the cylinder, would be pi times g of y squared. And so the change in the volume would be that times the change in y. And now I'd be summing up all those slices from C to D. And that will become our integral that we go and solve. All right, let's do it. So we're going to find the volume. It's just our parabola, y equals 4 minus x squared, and we're going to rotate it about the x-axis. Pictures just help visualize exactly what you're doing. As I say, I know how you love drawing your diagrams, but it really does help, because I can now visualize exactly what it is we're doing. Find the volume generated when the area between the parabola and the x-axis, so it's this section in here. I'm going to rotate about the x-axis, and in this case we're taking slices perpendicular, so it will be a vertical slice in there. And the thickness would be the change in the x value. If I was to rotate that vertical slice, we get our cylinder. The radius would be y, but I need it in terms of x because that's what the thickness is in terms of. So we change that to 4 minus x squared. So the area of the face, pi times 4 minus x squared squared. And delta b, whether you want to expand out, I suppose, there or expand out later, that doesn't really matter, delta x. So we want the limit as delta x approaches 0 from minus 2 to 2. We're going to take all those slices, add them together. Now, I can still use my ideas about symmetry when I create the integral, so I can say, oh, well, that's going to be twice the integral from 0 to 2. And the actual integration, you can see, I mean, it's very basic, this one. Add 1 to the power over the power. That's what I mean, in a lot of the 4-unit questions, it's not so much the integration that we're worried about, because a lot of it does turn out to be very simple integration. It's this process of setting it up. Can we get there? Some of the more involved ones, of course, have more interesting functions to integrate, hence why we've done all that work on integration. That one turns out to be 5, 12 pi and 15. But the advantage of this idea is we are no longer restricted to rotating around the y-axis or the x-axis. We can rotate around any line. So we're going to find the volume, same parabola, but now I'm going to rotate it around the line y equals 3. So same parabola, but I'm going to rotate around this blue line. So just this area here around the blue line. I'll need to know those points of intersection, of course, because I'll need to know which x values I'm going in between. And they turn out to be, as you can see, minus 1, 3 and 1, 3. My slice is going to be vertical to the axis of rotation. So I draw it, I still get a cylinder. The radius, however, is no longer the y value, though, because I'm starting at 3. The radius would end up being the y value minus 3. And so it'll be 1 minus x squared we'll end up using for this. So my area will be pi 1 minus x squared squared. Change in volume will be that times delta x. I'll be summing out slices this time from minus 1 to 1. And integrate. And again, I've used the idea of symmetry, twice 0 to 1 in this case. And I end up with our answer of 16 pi and 15. So it opens up a lot more that we could do. I suppose another way you could handle that question, if you really wanted to rotate around the x-axis, you could say, oh, well, let's shift the whole problem down 3 units and rotate around the x-axis. And of course, if you shift that parabola down 3, then the parabola would end up with the equation y equals 1 minus x squared, as we've got there. Now, this time, we're going to go in between 2 curves, y equals x squared, x equals y squared, and we're going to rotate around the y-axis, but we get a much more interesting shape. So there's y equals x squared, our standard parabola, and x equals y squared, parabola on its side. We're taking slices, well, it'll be horizontal, won't they? We're going around the y-axis, so perpendicular to that will be there. The point of intersection is 1, 1. So I've just drawn a little slice in there, delta y. When I rotate this, though, I'm not going to get a cylinder or a disc. I'll get a washer. Okay. So I've got a cylinder with a hole in it, if you like, but a washer. So the thickness, first of all, I've worked out the outside radius. Now, and this is why I like the diagram, so I can actually visualise what I'm doing. If I'm going from the y-axis, the outside radius, and I've used colour here also to help, but I'll be going to the red parabola to get the bigger radius. So my outside radius would be the red one, but I need it in terms of y, so rearranging that, I get x equals y to the half. The inside radius, I'd be going to the blue curve, and that already has x as subject, so we know x equals y squared. So my area will be pi times, well, the y to the half squared minus y squared. So similar to what we saw in previous volume questions, we don't square it, we square the individual functions and subtract those. And so it'll be times delta y to get our volume, what's sometimes called the element of volume, or the volume element. Limit as delta y approaches 0. This time we're going from 0 up to 1. 0 up to 1. And the actual subtraction when you tidy it up is just y minus y to the power of 4. And so that's what we're going to integrate. And there's our answer, 3 pi and 10. Let's have a look at a nice four-letter question. 1996, and this was their question. Shaded region bounded by x equals 1, y equals 1, y equals negative 1, and the curve x plus y squared equals 0. Now, I don't know if they wrote it that way just to confuse people, but when you look at it, all it is the sideways parabola, x equals minus y squared. They just wrote it all on one side. So there's x plus y squared equals 0. The region rotated 360 degrees. We're not going around an axis though. We're going around the line x equals 4. X equals 4. Region is rotated. The line segment S, and they drew in a slice for us so we can see exactly what they're talking about. Sweeps out, technical maths word here, an annulus. An annulus. Show that the area of the annulus is just a circle with a hole in it, by the way. Well, they've given us the answer, which I suppose is nice because should we not be able to find it, at least we can then go and do the next parts. All right. Well, there is my annulus, but not only my annulus, the whole washer. I've put the edge in as well. The inside radius I've called little r, and the outside radius I've called big R. Let's go and work out what they are, though, in terms of y. So they're back to this diagram. And this is why a diagram's good, because remember, I'm not going around 1, I'm going around 4. So my radius would start at 4. The inside radius then would stop at this edge here of x equals 1. So if we look down our shape, it doesn't matter. It's always going to be a constant 3. We're going from 4 to 1. It doesn't matter where we take the slice. It's always going to have a radius of 3. That'll be the inside radius. The outside radius. It is so tempting to say 4 plus the x value. But it's not. It's 4 minus the x value, okay? Because the x value over here is negative. So if you went 4 plus the x value, you end up with something less than 4. But clearly it's bigger than 4. So just because the curve's in the negatives, don't let it throw you. If the curve was in the positives, then it would be obvious. You'd look at it and say, oh, 4 minus the x value. It doesn't change just because the curve's over on the negative side. So it's 4 minus the x value. The x value, this is again where we've got to be careful, because if we rewrite this, x will be minus y squared. So I do actually end up with 4 plus y squared as the outside radius. Again, a good reason why I think a diagram helps. But remember, in the actual HSC, they gave you that diagram anyway. So you draw your lines on there and work out. Okay, let's work them out then. So the outside radius, 4 plus y squared. Inside radius was a constant 3. So we're going to have pi outside radius squared minus inside radius. Hopefully, when we expand all this out, they've told us what the answer should be. And sure enough, yes, we do get the required results. Okay, so we've got that. Hence, go and find the volume of the solid. Okay, well, I know the element of the volume, will delta V, will be that area times the change in the y value in this case. So we're summing from, and we were going from a y value of negative 1 up to a y value of positive 1. And looking at the picture, we do have a symmetric shape there. So I can go twice from 0 to 1. And we'll just integrate that. And there we go, 296 pi on 15. Okay, so this and washers. Now, with the Patel ones, again, I was a little bit mean. We're going to look at another method tomorrow called cylindrical shells. Some questions are easier to do with cylindrical shells. Some questions are easier to do with discs and washers. I might have deliberately put some questions in there that actually are easier to do with cylindrical shells, just to make the point where you go, oh, whoa, this is really, a lot of working out. And then when you look at it using another method, you go, oh, actually, wow, that's really quick. So.
Right.